thank you very much. And this presentation, where you can see all the authors, born from a joint research that we developed from Polytechnic di Milano and Bochum University, and vice versa. So we organized shared work together in the last month, and this is one of the results that we received, that we achieved together. So where we start? We start from the consideration that when we deal with construction, where we deal with buildings, one of the crucial point is, of course, the one of the cost, how much the building cost, how much the construction cost in general, and also dealing with the time, so how much time I will take to construct this. And we know that in construction, sticking with the time and the budget cost, it's something that is hard. We know that we work with 4D models, 5D models, so we have this integration, but basically when we use the available technologies and available software that we have today, still the connection between our 3D models and the elements related to cost and time is fragmented, because usually the connection is based on codes, and the software and let's say, our environment, our digital environment cannot recognize problems or issues in the connection between the elements, and cannot interconnect the different domains that we have. The work that we want to develop is about integrating these different elements, because when you start, basically it's like having 3 different domains. So the one of the geometry, where we put some information, we have all the information that we put in our, for example, IFC models, but then when we go with scales, for example, we use our software project, Primavera, whatever you want, and then still with the cost, maybe we use other software, we use an Excel, we use commercial tools that develop the cost elements, but then these are not really always interconnected, and we have one point that in both cases, so both in time and in cost, we should have the same resources, because basically when we are planning how many times we need to construct a building, you are thinking about people, machineries that are going into the construction site to build these, and the same it should be about cost, but this is not always the case. So usually when you plan, you don't really reason in the same way. And then there is a problem about updates, because many times these elements are not completely interconnected one to each other. So when you update the time, then you forgot to update the cost in the same way, then it's not really linked completely from one time to the other. So if you have a change of the cost, it's not always related to maybe a change in the geometry that you have. So when you have these, it comes to clear that we need in some way to find ways to interconnect these different domains. Also, we have a problem about how we develop these things. So we work in IFC, for example, or we work with different formats in our geometries, and then also with the other elements, we have always to work in different ways. So we experimented, for example, in a different research, how to work with cost integrated in IFC, but then integrating all together, it's not easy, and there is a really lack of semantic interoperability between the different domains, because people are talking about the same things in different ways. So what is the aims? The aims is to integrate these domains in a unified environment, considering the development of a resource-centric approach. So what we have done is that we developed a series of ontologies, and these were presented last week in the LDAC conference. So we developed an ontology based for the resource, an ontology for the cost, to combine these domains and try to find a way to put these in a way that also the machine can understand in the connection between the different domains. So basically, what we want to do is that at the end, once all the elements can be connected, you can query the information that you have integrating the different domains. So you can make queries that can start from the geometry and goes integrating the time and the cost related to the project itself, and vice versa. And this will allow, as we will see in the result, to make better decision, so to have a better decision-making process that can enhance what we have today. It will make possible to check the consistency between the different domains, being sure that you don't have a time that is not coherent with the cost and that is not coherent with the geometry, so that you can basically ask to the platform to understand if the cost that you associated to a specific element is coherent or not, but also in this case to ask if the time that you have is coherent with the cost and the resources that you put together are working together. So here you can see the previous works that defined basically the basis. As you can see, the new ontologies that we developed have been published and presented last week. And then we started with the work that was developed in the Bochum University about the ICDD web application, where we integrated the new work that we developed in this structure. So basically the methodology, so we started considering the development of cost item, time schedule, and IFC models. So this part remains basically the same. So that means that you can develop basically your time schedule using Microsoft Project, that you can develop the IFC model using the tool that you want, so integrating the different part. And then we integrated all these elements, so all these result in the ICD platforms. Then, in the second step, we created the relation between the different elements. So we interconnected the elements that comes from the time, from the cost, and from the geometry. And for the last step, we used this interconnected network to make queries. And we tested some different queries to understand where it can go and how we can achieve. This is, of course, one piece, as we will see, so some queries that we developed, but then this can be extended starting from this point. We started from a real case study, so this is a building that really exists. So it's a model that exists in the market, and we started just exploring one part of the structural model. So we didn't go too much ahead in the integration of the elements, but we demonstrated the work with a piece of this element. So the input data that we have is the geometric data, so the IFC model basically, the cost estimation, so we used the structure that was provided by the Lombardy region in Italy, because this is one of the bases that we use also for the construction of the ontology. We have our schedule data, so our Microsoft project. And about the resource data, basically these data are integrated both in the cost data and in the time. So when you develop the cost information, you have attached to the cost also the resources that characterize the cost, and the same is for the time. So when you define the time, you have the different resources associated to your, for example, Gantt chart in Microsoft Project. So all these elements basically comes isolated one to each other, and inside of the platform basically we created the semantic relation between the different elements. So we connect the geometrical data with the cost, with the time, and these are automatically then connected to the different resources that we have. So we developed 4 types of queries, basically divided into chapters. The first 2 are related to demonstrate that once you have finished, in any case you can obtain the result that you are already able to obtain in a traditional way, but also having the possibility to check the things. So if you want to know, for example, as we will see, if you want to know the total cost of the project, then you can have it. So once you interconnected all the elements that you have inside of the project, if you ask with our SPARQL queries the total cost of the entire project, you can obtain it. So you can ask to the tool to give you basically the sum. If you need to have the cost of a single element or a group of elements, still you can do this, and this is something that you can do with traditional tools. But if you want to compare, for example, the cost and schedule analysis, so if you want to compare if the information that you have in your cost analysis and the information that you have in the time analysis are the same, so if basically the people that are working in that side are the same, now you can compare it. So you can basically have a query that combines the geometry, the cost, and the time to understand if the information that you designed are correct or not. And the same is true in the case of, for example, having a solution where basically you don't have, for example, the information of the material resource connected to the task. You can ask how many cubic meter or quantity of a resource I need the next week, or in 1 month, or in 2 months, and so on. So just to conclude, we demonstrated how it works, and we tested the integration of the work that can combine the different domains. What are some of the limitations? Of course, in some way, the complexity of the query and the need of having high quality data that you have to input in the system. And one limitation, but that we are already addressing in some way, is the need to create this semantic connection between the different domains manually now, but we are working to understand if the integration of artificial intelligence can optimize the last phase of the process to guarantee the automatic or semi-automatic connection and creation of the semantic relation between elements. Thank you.